Okay, so today we're going to derive the one-dimensional heat diffusion equation for a material of constant thermal diffusivity. So to start, the equation that we use is the change in temperature over the change in time is going to be equal to the thermal diffusivity times the second derivative of the change in temperature over the change in position. And remember that the thermal diffusivity is the thermal conductivity over density times heat capacity. Okay, so we can model this using a uniform rod. So for the rod, let's just draw it here. And it's a three-dimensional rod. And we are going to break this up into sections and look at the heat diffusion just of the section. And that's this here. Okay, so now let's give this some values. So we can say that the entire rod is going to initially be at 20 degrees Celsius. And we can say that the left side of the rod is getting heated at 50 degrees Celsius, and then the right side is getting heated at 90 degrees Celsius, just for this example. Okay, so we can say that the length of this rod is from 0 to L. That's the position. So we can rewrite all of this information so we have it in terms of like our initial condition and the boundary layers. So we can write it that T, where X is at, this is any position along the rod, this is initially. So T is equal to 0. Let's make this, the time is equal to 0, is the 20 degrees Celsius, because that's the initial condition. And then for the boundary layers, we have where X is equal to 0 of any time is 50 degrees Celsius, and that's from the left side. And the temperature where X is equal to L at any time is going to be 90 degrees Celsius. So these are the boundary conditions. And then this is the initial condition. So then looking at the pink area that we had before, we know that heat is coming in and then heat is also coming out. And we can write this as Q left and Q right. And then using this information, remember that we're trying to find the total heat flow. So we can say that it's the net heat flow. And that's going to equal the accumulation of energy. Or rather, the total accumulation of energy. But right now, with all the information that we have this in terms of temperature. So if we want to relate temperature to energy, we can use the equation that Q is equal to the density times the heat capacity times temperature. So we can now rewrite this to say that Q, which is the total heat flow, is going to be Q left minus Q right. And we know this because if you look back up at the rod, the 50 degrees Celsius is going into the rod, so that's going to be positive in this equation here. And then on the right side, because the 90 degrees is also going into the rod, but it's going in the left direction, that's going to be a negative in this overall equation because we said that the heat is flowing from left to right. So that means that this is going to be flipped to the negative sign here. And then if we remember from the last video that Fourier's law is Q equal to the negative thermal conductivity times area times the change in temperature over the change in position. And we can evaluate this from the left and the right. This is going to be Q left and then Q right is the same way. And then this area is going to be the area of the rod, or the cross-sectional area of the rod, which is that pink section up here. Okay, so now we can put all these equations together. So remember that this Q right here is going to be equal to rho CT. So we have density times the heat capacity times temperature is going to be equal to Q left, which was, we said before, was the negative thermal conductivity times area times the change in temperature over the change in position, evaluated from the left, minus the same thing, negative thermal conductivity times the cross-sectional area, change in temperature over change in position, but evaluated from the right. So now with this equation, we can see right here that these two negative signs are going to become a positive. So we can rewrite that. And evaluating it from the left, this part's going to stay the same. But then we're just going to simplify these two negative signs here to be a plus. And it's still evaluated from the right. And now we can see that this plus sign here, if we go back to the picture, how these arrows are in the same direction, that's where that plus sign comes from as well. And then remember also that right now we are in terms of this cross-sectional area, which it is this part here, this cross-sectional area, and really we're trying to find, we still have like this whole entire change in volume here, or rather the volume's constant, but it's the volume of the entire thing. So we can multiply this by the volume, and then also this is going to change as time goes on, so we can put this all over dt. So now let's rewrite this again, because this section here, everything is going to be constant except for the change in temperature. So we can say volume times density times heat capacity, and then times the change in temperature over the change in time. And then this is all going to stay the same on this side here, like that. And then if we look back up at the drawing, the volume that we're really focusing on is this right here for this equation, this volume. So we have this volume is going to be equal to the cross-sectional area right there times this change in position of this box. So let's rewrite that. So volume equals the cross-sectional area times the change in x of that section times density times heat capacity times the change in temperature over the change in time. And now this section over here, we can rewrite this as well. So this K value is going to be the same throughout the entire rod because it's the same material. So we have K factored out, And the same thing with the cross-sectional area from the right and the left, it's the same as well. So that can just be A. And then what we have left is negative, I think I erased something there. The negative change in temperature over the change in position, evaluated from the left, plus the change in temperature over the change in position, evaluated from the right. So now, let's simplify this some more. So on this side, the areas are going to cancel out, and we can rewrite this that the change in position times density, heat capacity, change in temperature over change in time, equals the thermal conductivity times, we're going to rewrite this part as well to make it a little bit easier to read, the change in temperature over the change in position of the right minus the left. So now we can divide this side. We can take this value and divide it on both sides. So we end up with the change in temperature over the change in time is equal to K over density times the heat capacity times this change in temperature over change in position from the right minus the left. And this is going to be divided by the change in position. And then we can recall once again that this is really thermal diffusivity. So this kind of looks exactly like the equation we said at the very beginning, where the change in temperature over the change in time is equal to the thermal diffusivity times the second derivative of the change in temperature over change in position. So this is the final heat diffusion equation for a material with constant thermal diffusivity. So for the second part of this video, I'm going to simulate the response of a uniform rod through explicit finite differencing of the heat diffusion equation. So we can start by drawing another rod. And we're going to break this up into sections similar to the last time. And let's just assume that these are all the same size. So we can say that the length of each of these is delta x. So these sections, you can have as many as you want, but to count them, we can say that I is equal to 0 on this side here, on the left side, and then on the right side, let's pretend that there's 100 sections, but the I is just counting the number of sections that we've broken the rod into. So we can say that wherever you are along this bar is going to be your position, which is x. We can set that equal to I, which is the counter for the number of sections that we have, times delta x, which is how big the sections are. And then we also want to know the time along the bar. So we can say that the time is equal to n, which is a time counter similar to the I that we said was like the section counter. And we're going to multiply this by the change in time. So remember from earlier that the change in temperature over the change in time is equal to the thermal diffusivity times the second derivative of the change in temperature over the change in position. So we can write this using these terms by saying that the change in temperature over the change in time is equal to the temperature of I plus 1 to n. That's going to be, let's say that we're looking at this block, that is the temperature of the block to the right of the one that we're looking at. And we're going to subtract that from the temperature of the block where we want to look at. And this is divided again by the change in time. So now we know how we're rewriting the change in temperature over change in time. So this term is done, and then the thermal diffusivity is going to stay the same. Oh, this should be squared. So now let's see how we're going to rewrite the second derivative of the change in temperature over the change in position. So we can draw this. Let's just zoom in on the rod from earlier. So this section here is the one that we're looking at. So if we want to find the temperature here, this is Ti. The one to the right of it is Ti plus 1, and then to the left is Ti minus 1. So here, this part here is a change in x, or a change in position. On this side, from these two terms is another change of position. Then there's one overall. And these should all have the time counter on them as well. So we can say that for this red section, that the change in temperature over the change in position is equal to temperature of I plus 1 minus temperature of I over the change in position. We can do the same thing for the blue term. But it would be temperature of I minus the temperature of I minus 1 over the change in this position. So we can write this all together, and this is going to be the second derivative of the change in temperature over change of position. So we can, I'll just copy this over. This would be the right side. Oops. This is the right side. And then we're going to subtract the left side, which is in blue. And this is all divided over the total change in position, which was the green distance. So we can rewrite this again, just to clear things up a bit. And this is going to be the change in position squared. And then we have T initial plus 1 minus 2 T initial, and then plus T initial minus 1. These are all the temperatures, or rather the second derivative of the change in temperature over the change in position. So let's plug all these values into our heat diffusion equation, this one up here. So we said that for the heat diffusion equation, the change in temperature over the change in time, that's going to be the change in I plus 1 at some time minus the temperature of I at the same time over the change in time. And that's going to be equal to the thermal diffusivity times this second derivative of temperature over position, which we said was temperature at position +1, which is on the right, minus 2 times the temperature of the position of the place that we're looking at, plus the temperature at a position -1, which is on the left of where we're looking at. And this is over the change in position squared. So what we're really trying to find is this term here, which is the temperature at some time at the position to the right of where we are. So we can say that that is going to be this same thing. But we are going to multiply this by the change in temperature on both sides and then add over this temperature of where we are initially. So this is the final heat diffusion equation of a finite rod using, or with constant thermal diffusivity using finite differencing. But now we want to try to model this in Excel so we can rewrite this once again to make that a little bit easier. So when we take this equation into Excel, we want to limit the amount of variables that we have to use. So I'm just going to rewrite this in a little bit more simple terms. So this stays the same as the temperature where to the right of where we are at some time is equal to the temperature of where we are at some time plus, let's factor the position and the change in temperature out. So the change in temperature over the change in position squared. And then this can stay the same, this numerator part can stay the same as the temperature at some time to the right of where we are minus 2 times the temperature where we are plus the temperature of what the one to the left of us is, all at some time. So when we do this in Excel, this part here, this thermal diffusivity times the change in temperature over the change in position squared, we're going to say that this is R when we go into Excel. Okay, so moving over to Excel, remember that we have this equation. Maybe you can see it. It might be backwards, but I'm going to keep this in front of me so I can look at the equation as I go through this. But remember we had that the thermal diffusivity times the change in temperature over the change in position squared. We put we grouped all that together, and I said that when we go to Excel, we're going to say that this is R. So you can say that's R dot, and then this has to be a value that's less than 1. So for this example, let's just make it 0.1. So remember back from the very first example that we did with the rod, we said that the initial temperature, let's say Ti, was 20 degrees Celsius. And we said that the temperature on the left was 50 degrees Celsius, and then the temperature on the right was 90 degrees Celsius. Okay, I just realized that you guys couldn't see my screen, but hopefully this is better now. But let's make this variables. So this is the column. The left column is going to be the names, and then the values are on the right. So here's that all done. Okay, so now let's see how many times we want to do this equation. So this will be times. This is at initially, so let's say that we do this, let's go here, let's do it 10,000 times, just so we can see these values. So this column up at 10,000. and then here they are. Okay, so now we can say that when the time is 0, like initially, we know that this is going to be the temperature on the left. Oops. There it is. We can fill this all the way down. And over here, this is T initial. And let's drag this over. Let's go about here. And then this is going to be the temperature on the right initially. And this can get filled all the way down as well. Okay, so we have that this value here, these 50, and this value here, these are the boundary conditions from before, and then this is the initial condition. So we can say that like each of these cells, it's kind of like visually what the bar looks like. So each of the cells is a different position along the bar. So we can say that it goes up by 1 each time. That's going to be I. As I increases along the bar, I increases by 1, which is the position. Okay, so the temperature of this block right here, of where we are right now, is, if we look at our equation from earlier, it's the temperature as the initial temperature plus the R value, which is the thermal diffusivity times the change in temperature over the change in position squared. We said that was R. Whoops. Let's do this. Okay. And then that's going to be multiplied by the temperature of the temperature of the position on the right minus 2 times the initial temperature, and then plus the temperature on the left. Interesting. Okay. What did it change? Oh, I forgot a parentheses. Okay, cool. Okay, so now we can take this same formula and apply it all the way across the bar. And let's fill this all the way down like so. Now we can see here this kind of curve right in here where the temperature changes as time goes on. So then if we change this R value, and let's say that it's greater than 0.5, it would be bigger because the thermal diffusivity is higher. So if there's a greater thermal diffusivity, this R value is going to be bigger. And if it gets above 0.5, then we start getting negative numbers outputted in Excel. So let's just show that. So here's 0.5, everything still looks normal. Let's change this to, let's say 0.8. So here's the negative values. It has some calculation errors that makes it negative. So there's limits to what Excel can calculate for this question. So we can say that 0.5 is the critical value of what the thermal diffusivity times the change in time over change in position squared, what that ratio is. We can say that the 0.5 is a critical point. Just to see, if we do 0.51 and scroll down a bit, maybe here we get the negative values. So it's just kind of showing that there is a critical point to this, and how we can still model this in Excel.